we can start now.
Okay. So do you start, Miss, or me?
Good evening, all the students. Who is this? Kaisyang, you have entered the waiting room for this meeting. Okay. Okay, good evening, all of you. So to help you with your mass balance with EP analysis, so I invited Mr. Ricky Saputra. He is our Taylor's University graduate, and he's very well versed in design of capstone because he has already experienced it, and to the knowledge that he has worked on dehydrogenation of propane itself in his undergraduate, so he can give you more better feedback on mass and energy balance using EP analysis. So he will teach you all the 5 levels of EP, right, Ricky?
Yes, Miss.
Yeah, so he will be going through all the different 5 levels from level 1 to level 5. And for this semester, you are going to do until level 3. Then after you submit the report before the next semester start, you can, no, after the heat integration is done, next semester you can do other 2 levels when you go into the utility part. So I will now pass the session to Ricky to continue with his lecture, and then we will have question and answer session at the end. Welcome,
Okay.
Ricky.
Yeah. Miss, can you give the host to me because I cannot share the screen?
How to do that? Because you created it, right?
Yeah, but I give the host to you.
Okay. Security, where to go?
The participant.
Okay,
And then
multiple
more.
participants can share. Okay.
Okay.
I just click to multiple participants can share the screen.
Okay.
Yeah. Okay.
All right. So good evening, everyone. My name is Ricky. So as Dr. Rashmi has mentioned, I will be helping you on how to do the EP or economic potential analysis in your capstone project. So for the lesson here, the example that I'm going to take is for the production of propylene through propane dehydrogenation process. So basically, EP is just how much money you can produce from your process plant, as in how much product you produce minus off the raw material cost that you have. So generally, EP has 5 different levels. So the first level is just the basic. For level 2, we will consider the selectivity and the extent of your reaction. The level 3, it will be adding recycling and scale up. Level 4 is for your unit operation maintenance costs. And level 5 is for your utility and waste management plant cost. So after you did all of these 5 levels of economic potential, then we will only be able to analyze our economic. For example, like return on investment, break-even analysis, and so on. So the first one that we will look into is the EP level 1. So for the EP level 1, you should be asking yourself is that whether my product is in demand and whether it is profitable. And as maybe you have learned that in process design, we normally start from our reactor and go out to utilities according to this onion model. So let's start with our reactor. So the reactor has the reactant in and product out. For EP level 1 is basically how much the product you sell for minus off the raw material costs. That's just basically it. So in summary, it's just the product price minus the reactant cost. For example, here I have a few raw material costs. And then for this propane dehydrogenation reaction, I just take the price of my product minus off the price of the reactant. Here I put as 85% yield because this 85% yield is actually from literature. So you can get maybe in your process, maybe it is 80%, maybe it is 70%. So it varies from process to process. So with this, your EP level 1 is done. It's basically should be done during your feasibility study. After that, we will look at for EP level 2. This is where things get a bit more complicated. And then whether this selectivity will affect the main purpose of your plant, whether you want to produce the main product or you want to produce some other product as well. And lastly, could you benefit from all of this side reaction? Maybe you want to produce something else. So these are some of the questions that you can ask yourself in the EP level 2. So now for EP level 2, for this propane dehydrogenation example, in the first step, you need to find out what are the side reactions that can occur in your process. So for this example, these are the main reaction and side reaction that could happen. There are, in this example, I picked 3 reactions, including 1 main reaction and 2 side reactions. The option of selection depends on you based on your literature study or any books that I have mentioned before. And also according to your module, whether your supervisor or your module coordinator allow you to pick whether 1, 2, or 3, or how many reactions that you want as the side reaction. So after you select your main and side reaction, you should also know what is the expected operating condition for your reactor. All right, so we're moving on to the step 2. We need to see the selectivity. How does it affect the conversion? Okay, so for the selectivity, you can straight away take your value from a literature, or you can generate some model. So in this example, I have a few data from the literature. For example, here I have a propane conversion at 30, 35, and 39%. Each of them give different selectivity. Okay, so sorry about that. I'll repeat from the EP level 2. And at this point, you should be able to determine your step 2 to find your selectivity for each of the site reaction that you have. So this selectivity value, you can find it from literature or book that did similar or same process as what you are going to do, or you can compile up a table to make a model. So you can better estimate the selectivity with respect to conversion of your main product. Move your feed, does your feed straight enter the reactor? So for this example, I propane dehydrogenation reactor to be in the middle, whereby before that there is a column to separate butane in. You already know what process that you are going to do. So you need to know what your feed consists of. You can start off my to the reactor. Test. Can everyone hear me?
Yeah, Ricky, maybe you want to off your video?
Okay, I'll off it.
Yeah, so I think it will be like.
Okay, so I repeat from the EP2. Okay, so from EP2, again, we should be asking ourselves, are there any side reaction that can happen? Whether that this side reaction affect the selectivity of our main product. And then whether this selectivity of the side product affect our main product. And could you benefit from this side reaction. Maybe you want to produce something else other than your main product. Next one, we will looking into step by step how we can do EP level 2. So the first thing that we need to do is to find the side reaction that can happen alongside with your main reaction. So here I pick 2 side reaction with 1 main reaction. You can pick more. It depends on your process, whether it is a dominant, whether it will give you a major product or is it a minor product. So you need to have a grasp on your process. And by saying that, you should also know the expected operating condition for your reactor. In the step 2, we will looking at the impact of selectivity versus the conversion. So as there are so many side reactions, we assume there are a few side reactions from your processes. The selectivity of each product, you can get it from literature, or you can compile a table and develop a model for selectivity versus the conversion of your reactant. So here are some of the examples that I developed a few models to fit in better with the selectivity with respect to conversion. Again, this is optional. You can develop your own model or you can straight away find the selectivity value that you desire. For step 3 is for us to start doing the mass balance. So first thing that you should be asking is that whether your process will be entering the reactor first, or is there any other processes happening before your reactor? Maybe is there a distillation column to separate your feed? So for this example, according to this diagram, for my process, I have an initial distillation column before it enters the reactor. So it means that before you do anything with your reactor, you should be doing your distillation column first, as in the mass and energy balance. And after that, only you perform on your reactor. However, if your feed enters the reactor first, then you would not need to do the distillation column first. So it's entirely up to your process. All right. So the next thing that you need to know is what does your feed consist of? And you could assume that it starts off at 100 kg per hour of feed. Or you can straight away start with the feed that will produce the demanded amount per year according to your process. So here are my feed composition. So in this example, as I mentioned before, the butane will be recovered first, as it will be removed first before the propane enter the reactor. So the mass balance around the distillation column, it is like this. Now, for us to be able to do the mass balance around the distillation column, you should know how to perform the bubble and dew point calculation. These are the example of the bubble and the dew point calculation. So I'm not gonna go into detail on how to calculate this. It's basically a trial and error process. The aim is that for you to get the vapor fraction equal to the liquid fraction as in 1:1. It does not have to be exactly 1.000 to 1.000 as long as it's 1:1. It could be like you see on the screen, it's around 1.00018, something like that. Then you check, after you did this, you check whether your inlet and outlet mass balance is correct or not. Because sometimes when we do all of this, we just straight away proceed to the next stage without checking the mass balance, which could be dangerous. It could affect your other processes. So every unit that you do, you always need to check the mass balance every single time. All right, so these are the 3 reactions that I took earlier. which consists of my main reaction as the reaction 1, 2, 3 is the side reaction. From here, there are 3 different extent of reaction, epsilon 1, 2, and 3. Then based on the product and reactant, we generate the mole balance. For example, the hydrogen is produced at the first reaction and it is consumed in the second reaction. So it means that it is E1 minus E2. I know I write there E3, please ignore that. As for the methane, as we can see, it is produced at E2 and E3. So it is E2 plus E3. So whatever generated is positive and whatever consumed is negative. And as for the butane, it is not consumed and it is not generated. So in this case, we mark it as inert. Then based on the equation of selectivity, it is side product over the product that we desired. So for example, if you have methane, this would be the moles of methane over the moles of the propane that you have according to the selectivity equation. So for methane, it is E2 plus E3 over the propane, and so on for the ethane, ethylene, and propylene. So after you generate these equations, as I mentioned before, you have the selectivity with respect to conversion equation just now, if you decided to perform the modeling. So here are the value for the selectivity at each different propane conversion. So for the example here, I'm gonna take at 50%. So the extent of reaction, which is equal to the conversion of propane, so is as what you learn, Ca is equals to Ca naught times 1 minus the conversion. So we already know our feed, but remember our feed to the reactor is the outlet from the distillation column. So from here, we can get the value for epsilon 1 plus epsilon 2 plus epsilon 3. Now, for the E2, E3, and E1, here we are combining the selectivity equation that we have developed earlier with respect to the extent of reaction. So for E2, we have this equation according to the selectivity of C2H4. For E3, we have this equation for the selectivity of C2H6, and so on. From there, we can get the value for each extent of reaction. Now, the total of your extent of reaction here, the E1 plus E2 plus E3, and then E2, E3, E1, this should be equal to your initial propane feed that is entering the reactor and exiting the distillation column. If it is equal, it means that your mass balance is okay. So these are the inlet and the outlet in kilogram per hour based on the 50% conversion and the selectivity calculation with respect to the extent of reaction. So the inlet and the outlet total, they are the same. After that, you would need to calculate how much can you produce or what is the profit you produce. So from here, my products are what listed here, everything except the propane. So basically, you just times the mass flow rate with the price of your product. Now here, in additional thing, there are purge percentage. Purge, I will touch on it in a later section. Now for the next part, so after you found what is your inlet and what is your outlet of the reactor, we can do the costing as I mentioned earlier. So you repeat the process for every possible conversion. Here I tried from 0.1 as in 10% until 90% conversion. As you can see, all of it gives different value. And then you plot profit versus the conversion. Then you will have a parabolic curve, something like this. So based on this curve, we can see that the 50% gives the highest profit in the current example. As you can see from the table, it gives 195.75 ringgit per hour. Now bear in mind that this is your single pass conversion since we have not did any recycling yet. So for EP level 2, we stop until here. Now we move on to EP level 3. So for EP level 3, you should ask, for example, can I add a recycling stream to my design? From where and to where? Would the recycling stream affect your output? How will it be? And how much will it change in the feedstock by implementing a recycling stream? Now, from the EP level 2 diagram, we have a diagram of the PFD, something like this. Reactant in. Again, bear in mind, this reactant in is the product out of the distillation column. And then the product out. The product out will go to these separators. There are a few separators here, just that I did not show. I'm just going to show what I recycled back to the reactor. So the reactant in, it has the following composition, and the product out, it has the following composition as what we determined earlier. And after you did all the separators from the product out, you will have the recycling stream, the one that you desire. From here, my recycling stream consists of propane, propylene, and butane. The rest, it will be my product. So now we have this EP level 2 diagram. So we want to implement a recycling. So now, the recycling stream that I'm doing is from the top product of this separator. Basically the propane, propylene, and butane stream. I recycle it to the reactor and mix it with the reactant in. So of course, after the mixing, the stream after that will be different. The product you produce, the amount will be different. And also the one that's going to be recycled back to the reactor will be different than what you decided in the EP level 2. So how do we do this? To do this, I have give Dr. Rashmi an Excel iteration sheet for you to be able to perform iteration according to the recycling. So the Excel sheet consists of two parts. The first one is for the conversion of the consumed product, and the other one will be on the product that is formed, but initially there is an initial product. How much will it be in total? So now let's start doing the recycling. So we start from our EP level 2 diagram just now. So I'm gonna show you step by step on how to do this. Okay, so these are the Excel sheet that you will have once Dr. Rashmi gives to you. So this Excel sheet is made based on the diagram here. So stream 1 is the feed in, stream 2 is after mixing, 3 is out of the reactor, 5 is recycled, and 4 is the product. Now, in the recycling Excel sheet here, you can see the one highlighted in red. You only need to edit the one highlighted in red. The others, you don't need to touch them. Okay, so here, the first red highlight is the conversion of your reactant. The second highlight here is the amount that is recycled in percentage. Here is the equation, the amount of A recycled over A exit the reactor. MA1 basically just the flow rate that's going in, and same with 2, 3, 4, and 5. Okay, so let's do one by one. And yes, you need to do one by one for each of your reactant. Here, let's start with propane. So the propane here, for this example, I picked 50% conversion. So you put 0.5. Okay. Next, we look at the amount of the propane recycled. According to the equation here is the amount of A recycled over the A exit the reactor. So the amount of A recycled is, we have propane, is 46.0323 divided with A or propane exit the reactor, 46.1998. So the ratio that you will get here is 0.9964. Okay. Now, the propane that is entering your reactor. The propane that is entering your reactor here is 92.3996. And the amount of propane recycled is 46.0323. Okay. So if you see from the Excel sheet, at the beginning, they will give you a very different number until one point, the value converge, as in there is no more change in the value. So it means that your recycling has reached an equilibrium. So this will be your new stream. So let's make a new Excel sheet, the PowerPoint sheet. So now the propane that is entering your process or the reactor is 184.136. And then the propane exiting your reactor, it will be 92.068. And the propane that is recycled will be 91.737. With that, you're done for the propane. Now we refer back to the EP level 2 just now. Propane we have completed. Now let's go to propylene. Now propylene, at the reactant in, we have a bit of propylene. And at the product out, we have more propylene. As propylene is my product, so it means that propylene was generated. So refer to your Excel sheet for the recycle for the generated product. Okay. Again, there are 4 highlights. These are the only thing that you need to edit. For the first highlight, you need to see how much percentage of propylene you produce or the product you produce. The value should be more than 1 because your product will be more than your initial reactant. The equation here is the amount of A produced over the amount of A fat. So how much of propylene here produced? You produce 38.45112 divided with the amount of A fat, which is 5.04. So the ratio will be 7.629. Okay. How much percentage of it is recycled? As what we did earlier, is the amount of propylene recycled over the amount of propylene exiting the reactor. So the amount of propylene recycled based on the PowerPoint is 2.21986 divided with propylene exiting the reactor is 38.45112. So the amount that is recycled is 0.0577. Okay. The ratio that is being recycled is small. It is obvious because propylene is your product. You want to recover it. So if you have your product with a big percentage of recycle, it means something is wrong. Now we edit the other red highlighted cell. Propylene entering is 5.04. And the amount that is recycled is 2.21986. Again, look for the converged value. So the converged value starts from here. So you take that value and put it in your EP level 3 mass balance. So the propylene that's entering, which is the MA2 in the Excel sheet, it is 9.003. And the propylene exiting will be the MA3, it is 68.685. The propylene that is recycled, it is 3.963. With that, you're done with the second product or the second composition, propylene. Now you have the third one, the N-butane. So for the N-butane, we previously established it to be inert. So refer to the recycle, consume, or inert tab, and we are going to do it from there. Now, inert, as you all know, it's unreactive. So meaning the conversion will be 0. But there are some of the butane is recycled back. So there are a percentage recycle using the same equation. So the amount of butane recycled is 0.0125 divide with butane that is exiting the reactor, 0.01334. So the ratio will be 0.9370. The amount of A recycled and the amount of A. Then now you need to change the third highlight. The butane entering your reactor is 0.01334. And the one that is recycled is 0.0125. Okay, for butane, as you can see here, it takes a while for it to converge. But finally, it will converge at 0.1998 here. So we take that and put it in the EP level 3 PFD. So your butane, after mixing, it would be 0.212. And then the exiting the reactor is still the same, 0.212, because there is no reaction for butane. And the amount that is recycled is 0.198. With this, you're done for the butane, and you're done using the iteration Excel sheet. Now, we need to fill up the remaining column. For methane, as you can see, there are no methane, so 0, 0, 0, 0. For my recycling stream, also there are no methane, ethane, ethylene, and hydrogen. Then you did your total. However, remember the selectivity from your side reaction. There will be a value for your methane, ethane, ethylene, and hydrogen. we cannot do this by using the Excel iteration. So for you to be able to find the value of your side product, you need to do again your selectivity calculation as how you did it in the EP level 2. Since you already got propane, propylene, and N-butane, the other side product, you should be able to get it. And then after you got it, again, perform the mass balance. In the reactor, out the reactor, make sure they are the same. Now, some question may arise that what happens if your iteration won't converge? If your iteration does not converge, it means that your process has too much accumulation. And as you know, accumulation will not be good for your process and it will damage the piping and all of your unit operation. So you could implement purging. However, when you do purging, some of the production line will be lost and you will have a loss in the profit. So bear that in mind. Or you can do an initial separation to recover whatever product that can be recovered before entering the reactor. These are two ways if your recycling won't converge. This normally happens for the inert compound. For example, my N-butane just now, it took a while to converge, but at the end it converged. So you can pick purging or you can separate it at the initial stage. So after that, the same thing, you need to find the cost, which is the product minus your feedstock or your raw materials. Now remember that your product produced will be a scaled up from your level 2. Let's say for level 2, you produce 5 mole. After recycling, you will produce more by right, maybe 10 moles. But your initial raw material will be the same. So by doing recycle and through this concept, you can see that you can produce a higher profit using the same amount of feed. So by doing that, again, you plot your profit versus conversion. It should give you a parabolic curve. Now from here, apparently the 30% is more profitable compared to the 50% that we get from the EP level 2. So here for the EP level 3, you have 30%. So there's a difference between EP level 2 and EP level 3. Level 2, you are more profitable at 50%, but for EP level 3, you are more profitable at 30%. Since level 3 suggests that it's more profitable at 30%, so I pick 30% conversion for my overall conversion in this process. This is how you can justify why your process is operating at 30, maybe 50, maybe 60%. So with that, we are done with EP level 3. However, remember just now we start off with 100 kg per hour. Of course, for a plant to operate, we cannot use that small amount of feed. So you can opt to scale up. So as I mentioned, I use a 30% conversion. Here are the mass balance for the 30%. It's different than the 50% that I showed to you guys. So this is before scaling up. Before scaling up, my production is 68 kg per hour. But my desired production, according to your market analysis and my analysis, it's 54,000 kg per hour. So you should not touch your product. You should touch or you should scale up your feed. Because if you scaled up your product from the reactor, it will affect the other stream as well. So it's best you start from your feed. So here, my feed, I start with propane 92.3. So it's again a trial and error. To get to 54,000 kg per hour from 64 kg per hour, my scaling up ratio is about 602.8 times of the 100 kg per hour that I started off with. So basically, you just multiply it and try again on the mass balance just to make sure that it is balanced. Because if not, it will make the other unit operation not tally. So with this, EP level 3 is done. You can also optionally perform the EP calculation after you scaled up your process. So these are the economic potential for my process. In the event that you did not start from 100 kg per hour, maybe you are confident that you want to straight away start from the amount that is in demand, you can. But again, check the mass balance. The procedure are the same, just that this step 6 is not for you because it's for scaling up. So up until the EP level 3, you're supposed to be done in this semester as what Dr. Rasmi says. Now, before you continue to EP level 3, you need to ensure both of your mass and energy balance has been done for every major or minor unit you have. Because the next EP level, it will consider your unit operation major or minor. So assuming that you have done for the mass and energy balance, I'm gonna brief you on some of the EP level 4. Up until EP level 3, you only consist on your reactants and your product or your side product. For the EP level 4, you need to consider your reactor distillation column. What is the annual cost, especially the maintenance cost? To do this, you need to know what's the volume, height, diameter of your units. Then, is my separation process need to be how high? And then how many trays? What's the diameter for the separation processes? The annual maintenance, especially for compressor, if you have, since compressors are generally very expensive. And do you have a reasonable heat transfer fluid? Let's say your operating condition is -70. Do you have a fluid that can make your stream to go down to -70? As this will be included in your cost as well. Just something brief for EP level 4. In my design, I'm using a packed bed reactor. These are the volume and diameter equation, and the KRT here is the cost of the annual cost of the reactor, the maintenance cost to be precise. And then the compressor power. So after you calculate the compressor power, then you will use that power to determine the cost of your compressor. Then your distillation column. Basically, you are designing your distillation column. What is the volatility ratio? What is the minimum number of plate? What is the reflux ratio? The minimum number of trays, the diameter, the height. After you calculate all of those, then you can calculate the installation cost or the maintenance cost for your distillation column according to the final equation here. So after you calculate everything, and here are my results for the reactor, compressor, and distillation column. So these are the prices. So in EP level 4, you do not need to do the EP level 3 chart, the parabolic chart that you seen earlier. So you just pick the optimum conversion for you, pick the optimum profit, and you just minus off that profit with this annual cost. That's it for EP level 4. For the detail on how to calculate this, maybe Dr. Rasmi will give you on how to calculate them accurately. Now we're going to the EP level 5. So after each of your unit operation has been carefully designed, The next part is for you to see your utilities, such as your heat exchanger. That is the first one. And the second one will be your waste management plan. The waste management plan is like your mini plan of your overall plan. So you need to again design your waste management plan. Depending on your waste, you may need one waste gas management plan and waste liquid management plan. So it depends on your process. So for the utilities, maybe you guys have learned about pinch. So you need to ask yourself, have your pinch analysis been optimized yet? And then how much of the heat transfer fluid that you need for that particular heat exchanger or utilities? And then the waste gas management plan, what is the operational cost? And do you have a reasonable heat transfer fluid for the overall processes? So for the first part will be on the utility in the EP level 5. So these are the diagram show is the optimum pinch analysis